Hey guys, welcome to lecture. A couple things before we get started. I updated the schedule, so keep your eye on that because the schedule is going to have to be fluid a little bit because I don't know how this is going to be. I canceled lecture on Tuesday, the 17th, because BYU canceled it, and so we moved everything down to Thursday. Make sure you do all your assignments on time. But keep an eye on that, the schedule. I'll message on Slack if I change anything, but just make sure you watch that because we're gonna have to adjust based on lectures. Now we have extra lectures, and it's gonna be a little crazy. So, but yeah, just make sure you keep an eye on that. The other thing is, so I'm recording this down in my basement. I've never really recorded anything before like this. So if you have feedback, please let me know. Hopefully everything will go well and you'll be able to learn from this still. I'm sure there'll be some kid noises going on in the background. My son's room is right next door to the office, and so you might hear some screaming or banging on the wall or something, I don't know, or fighting. So I apologize for that. But, it is what it is. So let's get started. So first, what I want to talk to you about today was this protocol that I built called on-off noise power communication. I'm sorry I made you read another one of my papers. Like I said before, it's not the best paper in the world. It's just easy lecture and something I'm very familiar with, and I thought it would help illustrate kind of principles of Wi-Fi and how to abuse the principles of Wi-Fi. And so it's a good paper for this class. But yeah, so it's called on-off noise power communication, or ONPC, what I call for short, ONPC. Before we get going with that, I want to talk about the context behind why we create this protocol. As you probably know, I do air quality research. So I started out with this NIH project where we're putting air quality sensors in homes with people that had asthma. And so these were Wi-Fi sensors. We had 3 in a home. Typically they're in the living room, in their bedroom, and outside. So we wanted to get kind of understanding of how good the air quality was inside versus outside, but also where they spent most of their time. So living room or like TV room or whatever, and their bedroom. And so we had these 3 sensors. But what's interesting about this is, I helped build these sensors and program them, but I wasn't the one deploying them. It was someone else deploying them. Someone that wasn't really very technical or definitely didn't know anything about wireless networking. And so they'd place these sensors throughout the home wherever they need to, and they didn't know where the access point was necessarily. They didn't know how well the sensor was connected to the network. They would make sure the sensor worked before they left. So we knew that at that moment it was working, but as we learned quickly in this project, that things can change very fast. And actually that was the biggest motivation behind this. Is I built this dashboard. You can see a screenshot of it right here, showing what sensors are online, what sensors are offline last time we received data from them. And what we saw very quickly was sensors would just go offline randomly. Here in this instance in time, monitor B003 has been offline for 3 days. The third one down, monitor B016, has been offline for 5 hours. And so we'd sit there and be like, why are these sensors offline? Why has it been offline for 5 hours? And these were real participants. These are real people. And so we had to say, well, should we call the participant, or should we have someone call the participant and say, hey, can you check on the sensor? Should we send someone over to go look at it? Should we just kind of hope it gets reconnected? So not knowing what was going on was a huge annoyance, and actually could hinder the study, because if you have sensors that are not collecting data anymore, they got unplugged or something, they could negatively impact the study because now you're not collecting data. And so we quickly became familiar with this idea of these different problems that we could encounter along the way. And so here I have it on a spectrum of a less severe problem and a more severe problem. So something like a Wi-Fi disconnect. We're all familiar. Wi-Fi can be flaky at times, depending on how far away you are from the access point or your access point type. And that's a less severe issue. If it disconnects from Wi-Fi, we programmed our sensor to handle that such that it collected data, and then when it reconnects to Wi-Fi, it'll just send all that backlog data, even if, when it's connected to the internet. So it's annoying, but it's not a huge deal. Continuing on, it's like, well, a bug encode is definitely more severe. That could cause issues where there could be data loss. Hardware malfunction, that's where you're not collecting any data. But one of the worst is probably no power. typically what will happen is someone just unplugs the sensor from the wall, either purposely or by accident. Maybe it's connected to a power strip, and they just need it to charge their phone or to plug in their Xbox or whatever. So not connected to the power, and that's the worst. In my case, the worst problem, because now the sensor's doing nothing. There's no hope that it'll recover from this. There's no partial functionality it's doing. It's just dead. It's just a piece of plastic sitting there doing nothing. And so what we really want to know is, can we tell the difference between these different issues? Because they have different implications. Like I said before, Wi-Fi disconnect, it's annoying, but it's not a big deal. We'll still get the data. It'll be okay. But something that's disconnected from Wi-Fi, has no power, it's useless to us. It's not collecting any data. So that's a very much more severe issue. And so we'd love to be able to draw a line through this and say, okay, we know it's less severe issue. It's just disconnect from Wi-Fi, so it's okay. We don't need to bug the participant. We don't need to ask them to check on the sensor or send someone out to fix it. Versus if it's a more severe issue, then saying, okay, yeah, we need someone to go out and check on this. But the problem is, from the dashboard standpoint, from that page I showed you earlier, there's no way to tell the difference. They all look the same. Has that sensor that's been unplugged, disconnected for 5 hours, has it been unplugged for 5 hours? Or has it just been disconnected from Wi-Fi for 5 hours and it'll reconnect? So that's the big motivation, is how can a remote manager know if a Wi-Fi device is functioning or not, if it's been disconnected or if it's just a Wi-Fi disconnection. And this becomes especially bad for what I call a difficult to access location. So someone's home is definitely a difficult to access location, because you can't just go over anytime you want. You're bugging the participant every time you interact with them. We've had people drop out of a study like this because we're asking too much of them. So this is definitely a difficult to access location. And even if they are willing, it can take a week or two just to coordinate their schedule with their deployer schedule and go out and fix it. So this is not something that can be done very quickly or has a cost every time you interact with the participant. So we want to try and minimize this as much as possible. So we start thinking, well, why is this happening? So here we have a Wi-Fi sensor, air quality sensor, connected to an access point. And this sensor is on the edge of connectivity. It's at the lowest data rate the access point supports. You guys remember from Todd's lecture, right? That the access point chooses what the lowest data rate, so it could be 1 megabit per second. In this case, I said it was 6 megabits per second. And so the access point, that's the lowest data rate supports. And so the sensor's on the edge connectivity. But when the deployer went to the person's home, it worked. And so they're happy, they're done, and they move along. But what happens is the sensor that's on the edge of connectivity, if something happens to it, let's say like a laundry basket gets put in front of it, it's just something that will just weaken the signal just a little bit. All of a sudden the sensor will become disconnected. Just as a side note, this is literally what happened. My advisor was at home, and I was looking at all the sensors, and I noticed his was disconnected from the network. I said, oh, that's strange. Since I know he's at home, I'll just message him. So I messaged him to go check on a sensor to see what's happening, and he checked on it, and there's a laundry basket in front of it. He didn't think anything of it, so he moved the laundry basket and said, oh yeah, the sensor looks fine to me. I don't know what's going on. And sure enough, I checked to see, yeah, the sensor is fine. That's weird. And so then he realized, so he put the laundry basket back there, and sure enough, it got disconnected again. And so this is a laundry basket, which a wireless signal should in theory go through pretty easily, was just enough attenuation to cause the sensor to get disconnected. This sensor was on edge of connectivity. The signal to noise ratio was not very great. And so just one little change in the environment, like a laundry basket or someone moving a chair or a door closing or something like that, or furniture being moved, can cause the sensor to disconnect. And most sensors aren't on the edge of connectivity, but in a deployment where you have 10 participants and 3 sensors each, you're going to find sensors that are on edge connectivity. Especially our outdoor sensors were the worst because they're going through brick walls or whatever. They're always barely connected to Wi-Fi. So this was what we saw in our deployments. So, and it's kind of interesting how Wi-Fi works is it sets the lowest data rate. In this case, I said 6 megabits per second, could have been 1 megabit per second. It's up to the access point to decide. But if a sensor or a device is not able to maintain that lowest data rate, then it just is no longer connected. So it sets the lowest bound and then it's no longer connected, which, from Todd's perspective, that's a good thing, right? He wanted that so that it would reduce the range of these devices, so not as many people could connect to it. But at a home environment, you want everything connected to it as much as possible. You care more about range, not about the amount of devices you can support per access point. And so that's an interesting side effect of Wi-Fi. It just sets the lowest data rate, and if it's too low, if it can't maintain that, then it's just no longer connected to the network. So we want to fix this problem. So, well, what can we do about this? And so we looked at alternatives. We could say, well, let's just ignore Wi-Fi and just go with cellular. And that would have been a good option, except that it tends to be more expensive. Cellular hardware, both the hardware and the data plan is very expensive. And that isn't even a guarantee it's going to work, because some people in their homes have poor cellular connectivity. So cellular is not that great of an option. We could have gone with LoRa. We'll have a whole lecture dedicated to LoRa, and some of you are doing this in your projects. But LoRa is a long-range wireless protocol. We've mentioned it throughout the semester. That seems like a good fit. But you need another radio. You need different hardware, and then you need also a gateway associated with it. So where do you put this gateway? You could put it in the home. You could put it in the neighborhood. But it's not that clean of a solution. It costs a lot of extra money. And for these type of studies, money is actually really important, right? Because it's like, you only have $1,000. And so do you want to support, 2 participants at $500 each, or do you want to support 10 participants and collect more data and have your study that much better and only have each deployment cost $100, something like that. So that's the challenge, is we want to reduce the price as much as possible, and Wi-Fi is a good fit for that. The last option was 802.11 Halo. Sorry, 802.11 AH, called Halo. And this is a up and coming protocol that uses 900 megahertz, similar to LoRa, to extend the range. And all these solutions require extra hardware, extra cost. And Wi-Fi is just so cheap. Wi-Fi is great. It's deployed everywhere. Both the hardware is cheap. This module I have here in this picture is only $3. And the infrastructure is cheap because other people deploy it typically. So we could just piggyback on the home's network, which is good and bad. Wi-Fi is also really well understood. LoRa is a relatively new protocol. How well does it scale? There's all these kind of issues that we don't really understand. Wi-Fi, we understand the characteristics. It's been well tested. And so we have a good understanding of how to debug it and what's going on with the network when it's not working. So we really wanted to go with Wi-Fi. So the problem, though, the key problem here is that Wi-Fi limits the slowest data rate. So we thought about this, like, what can we do to get around this issue? We said, well, can we build a communication protocol on top of Wi-Fi that has a longer range than Wi-Fi? And why we need longer range is because this device here, the sensor, is on the edge connectivity. If we can just extend the range a little bit more, then these devices that were on the edge of connectivity will no longer be on the edge. They'll now be able to communicate or be connected or somehow send data. So that's why we want to extend the range of Wi-Fi. So how do we do this on top of Wi-Fi without changing the hardware, without changing the firmware, without adding extra cost? How do we do this? So we came up with this protocol called on-off noise power communication, ONPC. So let's go back to our context of the sensor disconnected from a gateway. Let's talk about the general intuition behind how ONPC works. So we know that the sensor or the client is disconnected, but even if it's disconnected and the client's transmitting data, we know that some of the signal will still be able to be received by the access point. And once we go back to the signal to noise ratio, we know that some signal is going to be there, but just the ratio is not high enough for it to decode and be connected, but still some signal is still getting there. So what if instead of decoding frames, we looked at the noise instead? So what if we didn't care about what the actual data was being sent? We just looked at the change in the noise floor, essentially. So when someone's transmitting, we could actually decode that. So here's what I mean by that. Is what if the Wi-Fi device just transmits Wi-Fi frames in a certain pattern? We don't care what that pattern is. It's just some pattern. So in this case, in the image, I have a green on, a short on, then a long off, and then a long on. Some kind of pattern. You could imagine almost even like Morse code could be an example of a pattern like that. What if the access point didn't look at that, tried to decode what these frames were, but instead just looked at the noise? Here I have this kind of crude representation of what the noise would look like. You would expect that when the device is transmitting, when the client is transmitting, the noise will just go up a little higher, not much, but a little bit higher in the same pattern in which it's transmitting. So access point will look at the noise instead of trying to decode it. And what this will allow us to do is allow the Wi-Fi device to send information at a much lower data rate. So once again, we're making this trade-off of data rate and range. We're going much lower data rate, but we extend the range. So ONPC is a physical layer protocol on top of Wi-Fi. It's the first that I know of any protocol that's a physical layer protocol, but on top of another physical layer protocol, which is kind of cool. So what the ONPC transmitter does is it sends out beacon frames. It really could actually be any Wi-Fi frame, but beacon frames are relatively harmless and just well known, and people tend to ignore them if they don't know what they're for. So it's not a big deal. So we send out beacon frames in a pseudo-random pattern. And what this ONPC receiver does is it measures the noise looking for that pattern. So it knows what pattern it should be expecting, the pseudo-random pattern, and it looks for that pattern in the noise. But the really great thing about ONPC is it's implemented purely in software. This is done all in the user space. No firmware had to change as a result of this, and we're able to extend the range of Wi-Fi using spread spectrum techniques. Okay, the data rate is really bad, 1 bit per second. I mean, so Wi-Fi is in megabits per second, right? We're going by lots of orders down to about 1 bit per second. So it's much, much slower. And we'll talk about why it's much slower. But for our application, it's okay. It's okay if it's much slower because we don't need to be able to send a lot of data. And we'll get to what we mean by that in a second. So here's the architecture, kind of how we imagined it, is that a Wi-Fi device, a sensor of some kind, would have software running on it, what we call the ONPC transmitter. And when it detected that it was disconnected from Wi-Fi, it would then go into the ONPC transmit mode. And it would send out messages using ONPC. So we don't expect ONPC to replace Wi-Fi. This is just to supplement Wi-Fi. So if Wi-Fi gets disconnected, we're still able to have some amount of communication at 1 bit per second. And then we have our wireless router, and then the ONPC receiver is connected to the wireless router through Ethernet. And it's the one that's decoding this noise measurements and determining if there's an ONPC transmitter out there or not. You could imagine that the wireless router and the ONPC receiver could be one entity, and they definitely could be. But we didn't want to make that a requirement because we didn't want to have to change anything about the Wi-Fi router for this to work. So we kept it as a separate entity, but they could be combined to one thing if you really wanted to. So how this works is on the transmitter end, you have some data you want to send. So in this example, it's a 1100. You have some symbol. So this symbol has 4 elements to it, or with spread spectrum, they're called chips. So it's got 4 chips to it, this symbol, a 1, a -1, -1, 1. In the real ONPC, this was much longer. I think it was 1023, so 1023 chips per the symbol. So much longer, but for this, we just had 4 chips. So you take this data and you multiply it by your symbol. So you did this in the homework, right? So you're familiar with it. When it's a 1, you just keep the symbol as is. When it's a 0, you invert the symbol. So this is common spread spectrum techniques, direct sequence spread spectrum. And so you have this waveform now. And normally what you would do with this is you would transmit this signal out here. But what ONPC does is it takes this waveform and converts it into beacons. Because we don't have direct control over the hardware, we can't send out whatever signals we want. We have to get around this by converting them into beacon frames first. And so if it's a 1, then that means transmit a beacon. If it's a -1, then it means we're going to be silent. That's where the on-off part of on-off noise power communication comes from. Is either we're transmitting, we're on, or we're not transmitting, we're off. So we convert all these into beacons, and then we take these beacons, this pattern of beacon frames that we're sending out, and we pass that along to the Wi-Fi transmitter. So Wi-Fi is completely oblivious that we're building a protocol on top of it. It's just transmitting out Wi-Fi frames. On the receiving end, the access point's collecting noise measurements. Now, access points are always doing that, right, for carrier sensing and for decoding frames. So it's just measuring the noise. And so what we do is we take these noise measurements, we run them through a limiting function, and I'll get to more what that means in a second, or later down in later slides. But we take those noise measurements, we run it through a limiting function, and then we multiply those noise measurements by a symbol, the symbol we're expecting. We multiply in sum, and that gives us a correlation. And we had talked about this earlier with the DSSS, but when the symbol matches perfectly with the transmission of that symbol, then you have a really high correlation. And so that's what's being shown in the last graph, is this high correlation when they line up perfectly with each other. And then we know if it's a positive correlation that we've received a 1, and if it's a negative correlation, that means we received a 0. And so we're able to, by correlating this and sliding this symbol along our noise measurements, we're able to get either a strong correlation and know that, okay, that means we've received a bit of data, or we haven't yet. And so we get back our 1100 is the idea here. One thing I did want to mention is here these noise measurements. You might be wondering, why does the noise measurements look like that? I mean, I just drew it kind of pretend, but the reason why the noise measurements isn't very clean is because there's other interferers going on, other transmitters. There's the what they call the noise floor of just the kind of noise that exists in the world from thermal noise and from other things. And because our signal's so weak, because it's so far away, you actually don't usually see the signal through the noise very well. So that's why I drew it like that, is because there's all this noise or the transmissions being added to the noise, and so it's not always clear that the transmissions is actually happening in the noise. So along the way, we ran some challenges I want to talk about. So these timing requirements, carrier sensing, and noise from other transmitters. So first, with these timing requirements, as you could expect, hardware is the timing of the hardware we want to use wasn't very great. ONPC is very time sensitive. When you transmit out data, it needs to transmit at that time, and so if it doesn't do that, then ONPC is not going to work. And this is especially hard because we're writing all our stuff in user space applications. So first we tried this with the Raspberry Pi, and we got terrible timing guarantees. As you expect, it's Linux. I mean, we could have maybe done more in terms of how we programmed it, but just kind of when we said transmit this frame, it didn't always get around to it. It took some time for it to get around to it, and we saw this huge distribution of these random delays we had to wait. So we switched over to an ESP8266, an embedded system. As you expected, worked a lot better. Still not perfect, but it worked a lot better. So meaning when I called transmit, there wasn't a lot of randomness in calling transmit and then actually sending the transmission. So the timing requirements was a huge issue I had to deal with, and so we chose this ESP8266 as a result of that. So now carrier sensing, you all are familiar with carrier sensing, right? And this was a huge issue for us. Is carrier sensing is great, we want carrier sensing, but for ONPC it's bad. We don't want that because it adds randomness now. So we had the randomness of the system, that's what I call timing requirements, but now we have the randomness of accessing the channel, so to speak. So when I call the system command to transmit this frame, it'll say, okay, I'll transmit it for you, and then you don't know when it actually is going to transmit it. It'll get around to it eventually. As we know, you have to wait at least diffs plus a random backoff, but you might lose that time and you have to wait another diffs, another random backoff. So there's this uncertainty of when I say transmit to the time I actually, the data actually goes out wirelessly onto the network. There's some time there. And disk itself would actually be fine if it was just diffs or just system latency. These two right here, that's why they're in yellow. It's because they would be relatively constant, and so it'd be okay. It's the random backoff is the challenge here. There's randomness now in our system, and so how do we deal with that? So we thought, should we disable carrier sensing somehow? And we decided against that, because then it wouldn't be MAC compliant anymore. 802.11 MAC compliant. We would be interfering with other people potentially, and it just seemed like a messy solution to just disable it. So we thought about how we could fix this. So let me show you an example why this is a problem. Let's say in scenario 1 we have a symbol, a 1, a -1, and a 1, and we want to transmit this out, right? So the timing matters here, right? What happens if that first part of the symbol right here gets delayed? We want to transmit out this time, but it gets delayed a certain amount of time. So it's shown right here, this red delay bar. If it gets delayed, it still works out. You're still able to transmit the two symbols, but now this is starting to look a lot different, right? We were expecting a 1, a -1, and a 1, but at the receiving end, it looks more like a 0, or sorry, -1, a 1, and a 1. So all of a sudden now the symbol that is expecting it looks a lot different. Or another example would be, maybe you have a 1, 1, -1 here. How the hardware works is if you're in the middle of transmitting one beacon and you ask to transmit another beacon, it will fail. It'll just say, oh, sorry, I can't transmit it. So what happens if this first beacon gets delayed a little bit, and then we go ahead at this, this interval and say, okay, go ahead and start transmitting the second beacon. It'll say, oh, I'm in the middle of transmitting my first beacon, and it'll just error out and say, so now we've missed it. So now a symbol that was supposed to be a 1, 1, -1 now becomes essentially a 1, -1, -1. So that's not good. We can't have this because it'll mess up our symbol and ONPC won't work as a result. So what we did to avoid this is we add padding. We say, well, this is not usual for this type of system. It's not that crazy of an idea, but it's not usual. We're going to add padding to this system so that if there is a certain amount of delay, it'll be okay. We'll still be able to deal with it. So we're not going to transmit back to back. This allows us to deal with a certain amount of delay, and it'll still work out. So that's how we got around this problem of carrier sensing. And once again, it's not perfect. We could have carrier sensing last longer than the padding, and then we could run into these same exact issues I just showed here in scenario 1 and 2. So the padding is not perfect, but it helps resolve a lot of these issues that we were dealing with typical carrier sensing. So if you had a really congested network and carrier sensing was delaying a long time, the random backoff was getting delayed a lot, then this would not help with that as much. But for smaller delays, it solves that problem. Okay, the last issue that I want to talk about was this nearby transmitters. So you can imagine if you have this really distant transmitter that you're trying to listen to, and then you have this other transmitter that you don't care about sending data right next to the receiver, it could really just blow out your listening. You have all of a sudden this high energy where you're expecting to just look at this low energy. So we wanted to help deal with that a little bit. So this graph here, the top part of the graph is our raw noise power measurement. So here at the beginning, no one was transmitting the data. No transmission was happening, and then we started transmitting some amount of data right here, and then what we call a powerful transmitter was transmitting. So all of a sudden, it just skyrockets the signal strength. And this isn't that strong of a signal, but compared to what ONPC is looking at, it's much more powerful. And so you can see here we receive some of ONPC right here. That the star means we received it. We have a high correlation here. It goes above a certain threshold. This is a correlation. But then all of a sudden, with this high transmission, it just blows it out, and we can't see anything. ONPC is transmitting during this time. We just can't see it because we have this powerful transmitter interfering with us. So to avoid this, and this is not a completely solvable problem. If there's enough interference, then ONPC won't work. So I'll just say that up front. But there are things we can do to mitigate this issue and try to deal with it. So what we did is we had this approach where we created a sliding window, and we used rank. That's a not very common statistical method called rank that is so simple it's kind of almost confusing. All you do is you take your numbers and you just assign one value to each number. So if you have 100 things, measurements, you just take the lowest value and you set that equal to 1. And then the second lowest value, you set it equal to 2. And you just give each value all the way up to 100. So that means for any samples, you're going to have 100 unique values, and they're all going to be equally spaced apart. So that's what we did with rank here. We had to do a little bit of more analysis here. We had to kind of filter, say if it's below a certain point, set that equal to -1. And we took our rank and we actually mapped it in the space of -1 to 1 space. And we had to do more than that, but at the heart of it, we're just ranking these values. So there should be just one value for each of these, and that helps smooth out the distribution so that these powerful transmissions that happen don't blow out our correlation, don't add too much weight to our calculation when we're correlating and summing these values together. It sets everything back down from the space of -1 to 1, and so these powerful transmissions now have less impact on the calculation. So once again, here's our the problem that we had here, just showing you that again. When we add this ranking method, or limiting function we call it in the previous slide, it smooths everything out, and now we're able to see our ONPC transmission in the midst of all this noise. We did have a false positive here. We had thought it did cross a correlation, did cross this threshold, and so we thought, oh, okay, ONPC is here. Of course, that's easily avoidable because we know ONPC is only going to be transmitting a certain amount of space. We knew it took a certain amount of time to transmit it, so we could easily filter this out and say, okay, yeah, that's not an ONPC transmission because it's not spaced out the right amount. So we could avoid it, but kind of from just the numerical standpoint, we do see a false positive here. But we're able to recover a lot of transmissions that we were not able to recover before. Okay, so let's talk about implementation. So the ESP8266, that's where we implemented the transmitter on. So that literally that device there. All we need from it though really is just the ability to send a raw Wi-Fi frame. So you could do this on a Raspberry Pi. We talked about why we didn't do that because of the timing. But if you got the timing working properly, then you could do that. We implement on there. There's the SDK for the ESP has I forget what it's called, but some function called like packet freedom, I think, where you inject a packet. So you give it the raw bytes of the data, the whole header and everything, and it just sends that out. So really low level. We had to craft our own Wi-Fi frame ourselves, with the header and everything like that, all in bytes as a byte array in C, and it just sends it out. There are some limitations to this in terms of the size of the frame. I forget, there's some limit on the size of the frame. And there's also a limit on how fast we can transmit out, but that's limited by carrier sensing. On the receiving side, we used Nighthawk ACU 1900. It's a relatively common access point. Not the low end, but it's not the best ever. And we did have to change the firmware of it. So let me explain, because I had said earlier that we didn't have to change any firmware to get this to work. And why I say that is because we just went from the stock firmware of the access point and we flashed, what is it called, DDWRT. We installed that on this access point here. So we did change the firmware, but we didn't change the firmware anything specific to ONPC. And so I still feel like we were able to accomplish our goal of not changing the firmware at all, because we did switch firmwares, but we didn't change the firmware specific to anything ONPC related. It's just still a firmware. And really all we need is the ability to receive those samples, the noise samples, in user space. And so this firmware offered that. If there's another firmware that did offer that as well, we could use that. We don't really need anything specific from a firmware. We just need the ability to receive the noise measurements. And so with this new firmware, we're able to SSH into our access point and call a function to get the noise measurements. So we do that through SSH and get a bunch of measurements, and then we're able to run ONPC on those measurements. Ends up that the receiver was the limiting factor why we could only send 1 bit per second. For any system, the two limiting factors could be how fast you're able to transmit the data and how fast you're able to receive or sample to decode those measurements. And our transmitter actually was able to transmit relatively fast, and we had a lot of flexibility with that. Our ESP, it was on the receiving end that when we called, give me the noise measurements, we could only call that at a certain rate. It was too slow, and so that's what led us to be just a bit per second. If we found firmware, or maybe we modified the firmware a little bit, and we could increase the rate at which we were able to get those samples, and our data rate could increase as well. So it was a limitation of our firmware, but for 1 bit per second, it still worked fine. But ONPC itself is actually, it's just a way to transmit data. It doesn't care about what you do with that data. So we had to build an application. We built what we call Staying Alive on top of ONPC. And so what this did is helped us detect if a sensor was online or offline, if it was alive or not. And so what would happen is a Wi-Fi device would detect if Wi-Fi is no longer connected from the network, connected network. If it's not, then it would start Staying Alive, the application. So using ONPC, it would transmit out just a 1, just saying, hey, I'm alive. And what would happen on the receiving end, the Staying Alive receiver would use ONPC to receive those samples and say, okay, I see the sensor is sending out a 1. That means that the sensor's still alive. Even if it's not connected to Wi-Fi anymore, we know if it's still alive. And so we could use this, a remote manager could use this to say, okay, I know I'm not getting data, I haven't gotten data for the last 5 hours, but I know it's alive. It's been alive for these 5 hours. Versus, I haven't received data for 5 hours and I'm not receiving ONPC. That means it got unplugged, or there's something catastrophically wrong with the sensor, some kind of malfunction of some kind. So that means the manager can, the remote manager can go fix it or send someone out to fix it. But ONPC just allows us to get insights into whether the sensor is still alive or not. Okay, so to evaluate ONPC, we first took it outside. We wanted to see, try to reduce the interference. There's a lot of Wi-Fi noise, right? This is at 2.4 gigahertz, so there's a lot of things going on these non-overlapping channels. So we went outside to help just try to reduce the interference, just to get the purity of ONPC if it would work from a fundamental standpoint. So what I did is I set my access point in this park, and I would just walk away from the access point with my little ESP sensor until it was no longer connected or not. And then I knew if it was no longer connected, then we've reached the range, where Wi-Fi is no longer working, and I'd just stand there and let it run, essentially. I probably looked like an idiot because I was just walking around this park with this little ESP device watching the LED because, it doesn't have a screen or anything like that. So I just had the LED where it would blink really fast when it was no longer connected to Wi-Fi. And so I was just walking around looking at this little blinking LED until Wi-Fi no longer worked. And so we had to go pretty far for this because it's in an environment where there's not a lot of interference. It has line of sight. We had to go pretty far. This is a park in Salt Lake City. So these are the distances we had to travel. Had to move to get it, so it disconnected from Wi-Fi. And this is right on the edge of Wi-Fi connectivity. So if you moved literally like a couple meters closer to access point, all of a sudden it would start working. If you moved a little farther away, it would stop working. And so these are the edges here. I had to do a lot of walking. This is actually pretty far to walk by myself because I'd have to set it up there and then walk back to access point to run this. And then, of course, it wouldn't work properly, so I had to go check on what's going on with the sensor. Okay, and did a lot of walking, and it was fun. At least it was nice weather outside. Got a lot of exercise that week or that month that I was doing these experiments. So as a result of all these different locations, we were able to have an 85% symbol reception rate. So that means Wi-Fi was no longer working at these locations, but we were able to receive 85% of the time. We had a 4% false positive rate. So there was times that we thought we were receiving ONPC, but we weren't. Like I said earlier, we could do a better job at filtering that out. I guess I leave that to future work. But 85% is pretty good. I mean, it's not perfect, obviously, but it's pretty good for our application of staying alive. We don't need to know if the sensor's alive all the time. We just need to get the message periodically. So out of an hour, if we see that it's alive, 5 times, that's enough, even if it sends it out 60 times. So we're okay with the not perfect symbol reception rate. Okay, but we want to see how much further can we go than Wi-Fi? So we chose location 5 here. And so let's go beyond what Wi-Fi is capable of, because this is just right on the edge. So we did a couple more locations. Location 5C is the furthest we could get because there's a fence. I don't know if you can see that. There's a fence right here. And so I wasn't able to go beyond that because I think that was private property at that point. So I got as far away as I could. I can't remember, but it's in the paper in terms of how much further it is than Wi-Fi, or than location 5. But even at that point, we were able to have a pretty good reception rate. Of course, it went down because we're getting farther away, and the false positive rate went up. But still, we had 72%. So I think we could have even gone farther than Wi-Fi, even farther than what we did here in these experiments. So that was to help us understand that, yes, we're able to get past the range of Wi-Fi. So now we want to test this in a real home environment. So what we did is I lived in a small apartment at the time, so that didn't really work very well. So I went to someone's home, and we placed access point down in the basement. We wanted to get kind of the edge of connectivity. So, where would place access point in the basement, kind of the worst case scenario, and then we had a sensor up on the third floor, essentially, second floor of the home, but 3 floors away from the basement, on the opposite side of the house. And there was interference going on here. We had 5 neighbor access points, so not terrible, not like an apartment, but still there's plenty of interference going on the same channel. And we tested this out. Let's see, we were able to get 51% reception rate. So once again, not great, but for ONPC, for staying alive, it's perfect. It's exactly what we need. We just need to know occasionally if a sensor is online versus not online. Okay, so those were the 2 environments. So this is a much more realistic environment. It still works great. So now we want to look at, well, what if we have like multiple ONPC transmitters that want to transmit all at the same time? So we did up to 5 transmitters. And you can see as we add more transmitters, on the y-axis here is the percent of received symbols. And so as we add more add more transmitters, the percentage of received symbols goes down considerably. Like I said already, to support 5, that's pretty good, even at that rate. What is it? Around 30 or 40%. It works great for our application. And we did have to do some amount of work to get this to work properly. In the paper I mentioned that we used orthogonal codes. So each transmitter is sending out their own code or their own pseudo-random pattern, and these patterns are orthogonal to each other. So that means they shouldn't interfere with each other. It's not quite perfect. It's not quite like CDMA, code division multiple access. Just with how the signals combine here, it's different than how they do in code division multiple access, because we only know if things are on or off. We can't actually add the signals together. So it's a little bit different. So that's why you see this drop. Whereas if it was true code division multiple access, you wouldn't see this drop. But because we're not doing that purely, then we are seeing this drop. Last, we want to see, well, we're sending out a lot of Wi-Fi frames. How is this going to affect, just normal Wi-Fi communication? And we found it actually only affects Wi-Fi on very specific cases. Lots of other cases it doesn't work. So we had 2 setups here. We had access point, and we had an ONPC transmitter transmitting ONPC from far away from, where it's on the edge of Wi-Fi connectivity. So that's our common setup. And then what we did is first we put another Wi-Fi client, so now our third entity in this experiment, a laptop, close to the access point. So that's this graph right here, where the Wi-Fi client's close to the access point. And we ran 3 different configurations with that of different data rates. And then we said, let's take the access point now the Wi-Fi client far away from the access point. And so we took it far away and looked and tested out the same data rates. So you can see that, and then the blue bar is with normal. So just we ran iPerf, great tool. If you haven't ever used it, it's for measuring the performance of a network. It will just send us at a certain data rate. Using UDP or TCP or whatever you want. So it's a great tool to use. Here I was using iPerf, sending UDP. I didn't want to deal with TCP, right, with its retransmissions and all that stuff. I just want pure data rate, so UDP. And you can set the data rate of iPerf. So I sent it to what's called unlimited. Just send out as fast as you can. I set it to 5 megabits per second and then 1 megabit per second. And so under all these configurations, these 6 different configurations, the only time that ONPC really negatively affected the data rate was in this case here, where the Wi-Fi client was close to the access point and it was sending as fast as possible. So we have about a 20% drop in data rate here, which is significant, but I would argue that's not a really realistic case, because not very often are you sending unlimited data for a long period of time, right? If you're streaming Netflix, like we talked about before, it tends to be bursty, right? So you buffer all this data, and then maybe you run out of your buffer, so you pull more data and you buffer it again, and so it tends to be a burst. Whereas this is unlimited data for, I think, a minute or 5 minutes or something like that, where I'm running it. And so if you're running for unlimited, sending as fast as possible, then of course ONPC is going to interfere with you because it's going to transmit. But I should be clear, it's not interfering. It's just using carrier sensing. And so you're going to have to share the channel periodically. So it's not doing anything that another client wouldn't do. So it's not being destructive in any way or interfering. It's just doing normal Wi-Fi type things where it's using carrier sensing. So only under that condition where there's a drop. Any other case, you're not using the maximum data rate, and so ONPC and this transmission that you're doing actually can fit in really nicely together and has very little impact. Here, why using unlimited, why you don't see it drop really at all, is because the loss on the channel and the lower data rate of what Wi-Fi can support is the limiting factor here, not ONPC. And so that's why even on a unlimited from far away, you're not seeing a drop. It's because ONPC is actually having little effect. It's the loss on the channel and the other things that are having a bigger impact, and so you can't see it as much. Yeah, so that's the effects of ONPC. So in conclusion, ONPC is this protocol that we built that's only done in software to extend the range of Wi-Fi. It has lots of different applications. I talked about one, staying alive, where an IoT manager can just know if a sensor's online or offline. But there's other use cases as well that I didn't explore. And there's a lot of cool things we could do with this, actually. So there's just sending raw data for some reasons. There's interesting things you could do with this with other wireless protocols. Everything I've talked about isn't necessarily Wi-Fi specific. All we need at the transmitter is the ability to transmit energy or some kind of frame. It could be Wi-Fi, it could be Bluetooth, it could be cellular, it could be LoRa. And on the receiving end, you just need a device that can just receive the noise. So really, there's nothing Wi-Fi specific about this then. I mean, the context I presented this was Wi-Fi, but why not apply this to LoRa? Why not apply this to cellular or to Bluetooth? So that's part of the future work we're working on. Or it'd be kind of cool, they call it cross-technology communication, where a Bluetooth device communicates with a Wi-Fi device or vice versa. This would make it possible now because we're just looking at energy. We're just transmitting out energy and looking at energy. That's all we're doing. We're not actually trying to decode the frames. And so there doesn't have to be any kind of acknowledgement of what kind of modulations you're using. So that's it for ONPC. I hope you found this interesting. I think I went a little bit over in terms of my time. But if you have any questions, I think the two ways to have questions will be message on Slack. If you have questions, I think you can put the timestamp of what you have the question on, for the moment you have the question for. Or the other thing would be I'll be on Zoom during my office hours, most likely. May have to be flexible on that because we're having a baby soon, and so maybe I won't be able to there when the baby's born. But I definitely can be on Zoom. You can ask me questions in person, and we can go over the slides together if you feel like you want to do that. But yeah, so feel free to ask questions. And thank you. I appreciate your time.